Hi, I'm Dietrich, President of International Time Machines, and welcome to our video about clock frequencies. We wanted to understand how the design characteristics of a movement and the performance characteristics of a movement could be brought together to tell us exactly what's happening inside a clock. Along the way, we came up with some very interesting findings. I hope you'll agree.
We hooked up a sensor near a pendulum of a master clock, and over the course of an hour we tracked the regularity of the swing. We plotted the data over a 1-hour period, and it looked like it was a pretty accurate clock, dead on. But when you take a very close look at the data, you see that there are fluctuations which are cyclical in the performance of the clock. Inside each clock movement there are gears and shafts that are put together in combinations known as gear trains. There are several different gear trains in most clocks, and they each have a specific function. At the heart of most clocks, the regulation controls the speed of the clock, while the hands train drives the minute and hour hands, and the power train converts the weights into swing pendulum energy. Looking at the front of a movement, you can see the regulation train pinions down the center, and the power train pinions off to the right. Each shaft is designed to spin at a unique speed, and each has a large gear and a small gear with a specific number of teeth on each gear. In our ITR master clock, we see the shafts having a range of speed between 60 revolutions per hour down to 0.075. It's a huge range of frequencies, with the fastest being 1,000 times faster than the slowest. For any clock, you can calculate the design speeds or frequencies for the pinion speed of rotation as well as the teeth contact. As an example, in the first row we have shaft number 1, which happens to have the escape wheel that spins at 60 revolutions per hour. The large gear has 1,800 engagements per hour and the small 480. Since gears from different shafts mesh together, you'll see that for every shaft combination there are 2 gears that have the same speed or frequency.
So now that we understand you can look at a clock movement's design frequencies, let's take a closer look at how that can be brought together with some of the performance characteristics.
Returning to the data that we captured from our clock over the course of an hour, we want to identify a repeating pattern in the data. It's easy to see that there's a recurring or cyclical compression of the data points at a regular frequency. If we measure the gaps, we see that they're occurring every 14 minutes and 40 seconds, or approximately 4 to 4.5 times per hour. We can find the design frequency that matches that clock anomaly of 4 to 4.5 cycles per hour. The source of the frequency is the contact point between 2 specific gears. We can identify the exact location in the movement that's causing that fluctuation. Turns out it's 2 teeth in the power trains that were cut a certain way to cause that fluctuation.
So clearly there's a correlation between the design frequencies and what we can see in the performance data. But how do we really look at that performance data in more detail and learn something from it? Let's take a look at that.
The next question became, how do you take a jagged line like this and understand what's causing the fluctuations? How do you break it down to the component frequencies? Fortunately for us, there is an algorithm that takes a signal over a period of time and breaks it out into its component frequencies. Not only does it tell you what frequencies exist, but it gives you a relative magnitude of each of those frequencies. When we apply the FFT algorithm to the clock data that we have accumulated over an hour, we have over 4,000 data points, and it highlights in the analysis less than a dozen key points that have unique characteristics. They're found at frequencies of 30, 60, 64, and 120, and over on the right at 330 to 450 as well. And compared to all the data points, they're significantly higher in value for impact of accuracy. When you look at the frequencies having a high impact and compare it to the design frequencies, using 30, 60, and 64, you can find their component counterparts perfectly in the design frequency chart. While frequencies of 30 and 60 can be passed off as coincidence, 64 is a very unique finding on both the design and the performance characteristics chart. By using the approach of clock frequencies, you can get a statistical number which is both measurable in detail as well as trackable over time to see how it changes with corrective actions. Further analysis is underway to better understand the sources of the 120 cycles to 450 cycles anomalies. But it's very interesting to note that the two collections of data points are mirror images of one another, pointing to a potential cause which is related by some frequency. So in conclusion, all clock components have unique design frequencies. Pinions have cycles per hour, as do gears, and they can easily be calculated from a design point. With accurate tracking, you can spot the anomalies and calculate their frequencies. You can look up your anomaly frequency on the design frequency table to identify the failing component. And it might be caused by a pinion that is bent or needs polishing, or a bent gear or tooth. Finally, a summary of the test equipment that we used includes an HP 5335 universal counter, a magnetic inductive sensor, a PC with Microsoft Excel for the FFT analysis, as well as Keysight software, and we did it on a ITR master clock with a mercury pendulum running at 60 beats per minute.
Thanks for watching our video about clock frequencies. We look forward to finding new ways to take modern technology and apply it to 100-year-old master clocks to learn more about their design and their performance. We hope you'll catch some of our other videos on YouTube and on internationaltimemachines.net. Thanks for joining.